All right, so let's start today's ASTRODEBATA. Let me introduce to you our guest today, Sarah Martell. She's coming from Australia, from University of New South Wales. With Sarah, we've been working on the GALAH project for more than 10 years now. So it's finally our pleasure to have her here in Ljubljana for the first time. Also, help yourself to Tim Tams. We have we're on topic with snacks today, so yeah. All from Australia, our guest, and today's snacks. So please, Sarah.
Thank you very much. So I was going to say the same thing, actually, is that I've known Tomasz and Janusz for like 10 years through projects, and I've never actually been here before to visit. So I've been having a really nice week. Thank you for letting me come and hang out and talk a bit about one of my favorite topics, which is globular clusters. So before I get going, I want to say that I'm happy if you interrupt and ask questions at any point. Like if we end up on some sort of tangent that's really interesting to everyone, then I'm perfectly happy with that. So my interest in globular clusters is a very classic sort of spectroscopic Milky Way, almost, well anyway, kind of view of globular clusters as a present-day object to be looked at. But of course, at the moment, they're having kind of a renaissance. And we think we're seeing them at very high redshift, and we think we're able to form them in cosmological simulations. And so there's a fun sort of convergence between the very local and the very distant that I think is happening with globular clusters. And so one of the things that I'll be talking about here is how they can be useful to understand the assembly history of the Milky Way and potentially, spiral galaxies as a group. So globular clusters, of course, are very old. They're satellites of bigger galaxies, all of that. But one of the things that's really puzzled us for a long time about them is that the abundances are not well behaved. So they tend to have a single metallicity, although the more we look, the more clusters have two or a range or something like that. Don't worry about it. But one of the things that all of them show is this anti-correlation within the light elements. So about half of the stars in any given cluster have perfectly normal scaled solar halo-like abundance patterns. And the other half are enhanced in helium, nitrogen, sodium, aluminium, maybe silicon, depleted in things like carbon, oxygen, fluorine, and magnesium. And we've known this since the 70s. We have not figured this out since the 70s. For a long time, we thought if we just take more data, right, we'll figure this out. Like maybe there's a pattern here and we're not seeing it. And if we collect all of the information, that somehow we'll figure out why in a group of stars that are basically all the same age, that basically all formed at the same time, something like half of them look like they've received chemical feedback from something doing hot hydrogen burning. But we have no models that explain all of these things simultaneously. So what I mean is, in terms of the anti-correlations, if you plot for a single cluster abundances like carbon versus nitrogen, about half the stars are here, which is normal, sort of where normal halo stars at that metallicity would be. And the same with oxygen. And then the other half are up here. They're depleted in the carbon and the oxygen. They're enhanced in the nitrogen and the sodium. And so we tend to think of these as sort of these curves as this characteristic shape for the abundance pattern in globular clusters. And if instead of looking at one cluster, you look at 19 of them, because you have lots of VLT time, what you find is that the oxygen-sodium pattern happens everywhere. Every cluster you look at, modulo, again, there are a couple of exceptions, but this is one of the problems with clusters, is that every rule you come up with, you can immediately think of an exception. But the extent of that anti-correlation is different in each cluster. So it's there, there's always a normal group of stars and a depleted, enhanced, anomalous group of stars. But the degree to which that enhancement and depletion has happened is different in every cluster. Perhaps this says something about the mechanism for that chemical feedback, but there's not an obvious systematic pattern to be found there. So the trick is, right, that basically every globular cluster does this, but there are exceptions. And when I say every globular cluster, what I mean is within the Milky Way, where we've observed a significant number of stars and successfully measured abundances. So when you look at Andromeda, that's too far away. We already can't measure the individual elemental abundances for the individual stars, but we are projecting. We're putting ourselves at the center of the globular cluster problem and assuming that everyone else's clusters behave this way. You can actually do this within like local group dwarf galaxies, but it's complicated. It's like difficult to get the data because they are, being more distant, it takes longer to get a decent spectrum and work it out. It appears in the Milky Way that only globular clusters do this, which is another thing that's really interesting that says that perhaps their formation is somehow unique, is that they're an environment that produces this anti-correlation pattern somehow. And again, perhaps that will explain how this happens, but we so far haven't managed to put that puzzle piece together. One of the tricks to trying to come up with a model for this is that every cluster is different. There's not a clear correspondence between, for example, the metallicity or the present day mass and the amount of anti-correlation or which elements are involved even. So the magnesium, aluminum don't always play along. Not obvious why that's true. And I mean, there are some patterns, but it's not as clear as you'd like. And then also, yeah, there are these correlations, but one of the tricks about this, and one of the things that the Milky Way globular cluster stars community has to really learn and to really sort of integrate into the way our thinking about this goes, is that the present day globular cluster is not the original cluster. And so we have a mass now, right? And we have an orbit now, and it's part of the Milky Way now. But it's one of the oldest things in the entire universe. It formed in an extremely different environment, possibly not even as part of the original, like the main progenitor of the Milky Way. And there's been a lot of time and experience since that point. And so if we want to understand the actual original properties of the cluster, those might be quite different to what we see at the present day. There's a lot of mass loss, for example. There's a lot of dynamical evolution in the way that the Milky Way has been constructed from smaller things. And so looking at what we have today, of course we don't get a clear picture of how clusters formed because we're not looking in the right place. But how do you look at the original globular cluster? So there is a lot of mass loss from clusters, right? They are gravitationally bound, they are dark matter free, they're satellites of the Milky Way. And so there are a number of processes that can cause stars to evaporate from them, and so we see big tidal tails. These are two nice clear examples of Palomar 5, which is an extremely well-known set of big extensive tidal tails around a cluster. That's just a density contours for star counts. And Omega Centauri, which is a slightly provocative choice because is it a globular cluster or not, is a favorite debating topic. It's one of the ones with complex metallicity distribution, and so we tend to explain it away as actually a nuclear star cluster. But we observe it as a globular cluster in that it's a satellite of the Milky Way that is probably dark matter free and the right mass and size. So there are actually a number of classes of objects, like a number of origins, that wind up being observed as the same type of thing today, which is another thing that makes it really hard to figure out what's actually going on. If you go and do, with Gaia, we have been able to go and do a very thorough mapping of streams across the sky. And this is one of the maps from Mahan, from Rodrigo Abada's group in Strasbourg, where streams are everywhere. Well, once you start looking, once you're able to get to a low enough surface brightness and you're able to get enough kinematic data to find the objects that are, the stars that are moving together across the sky, what we find is that there's lots of places where stars from dwarf galaxies and also from globular clusters are currently escaping and becoming halo field stars. And so for the stars with normal abundances, they just go become anonymous halo stars, right? But for the stars in that second group, that are depleted and enhanced and anomalous abundances, they'll stick out in the halo. If you can find the abundances for them, you can then figure out how many stars from the halo actually started from globular clusters, which is the point of the project. So we first tried this in, in Sloan data quite a long time ago. The idea there, we decided they had fairly low resolution spectra, and we thought, well, if the carbon and the nitrogen are acting like globular cluster stars, and the carbon's depleted, the nitrogen is enhanced, what we'll see in the spectrum is that the CN and CH molecular features will be strong and weak, respectively. And so we went and took, loads of segue spectra of things that look like halo red giants and measured band strength indices to work out proxies for abundance, and divided our data set up by metallicity because the actual correspondence between band, molecular feature strength and abundance is modulated by metallicity and temperature and things like that. And so for each little bin in metallicity, there's this trend that has to do with molecular dissociation as the stars get warmer. And the trend is a little bit different as a function of metallicity, because as you have fewer metals overall, you make fewer double metal molecules. Anyway, details. The point is, most of the stars behave like normal halo stars, which is good because they are halo stars. But a small fraction of them sit up higher in this space, so they're nitrogen enhanced, presumably. Their CN bands are stronger than the normal stars. And so we're able to choose a sample of stars out of here, a few percent, that are both high in CN, but also depleted in CH. And I'll give away the punchline a little bit, but these guys here at high metallicity, not actually very depleted in CH. So those are one of the questions that we need to come back to in the future, is what is going on with those stars. If they're not carbon depleted, why are they nitrogen rich? What are they? Where do they come from? Are they a whole separate thing? So we did this, like I said, quite some time ago now, and it kicked off some follow-up studies, which has been really fun. There's been, of course, we do a bunch of stellar surveys. We measure a lot of abundances in the galaxy, and then you can go looking in your favorite data set to find more of these. So we went to the Apogee data set once that became available, and we looked at nitrogen and aluminium and found, so the blue and purple are globular cluster stars, and the red are the halo field stars that we believe look like globular cluster stars in this abundance plane. Ricardo Schiavon in Liverpool did the same thing with Apogee data again, but looking at the inner galaxy instead of out into the halo. He was looking in to what is probably the inner halo, but might be the bulge, who knows? They're in the same place. And again, if you put the globular cluster stars in the different colors, you can see that they cover this wide range of nitrogen abundance where normal halo field stars don't. And so you can pick out the halo field stars that sit above that group and go, hey, those, chemically look like they came from globular clusters. And then you can try to work out what does it mean. And then again in Apogee, Danny Horta went and did a similar thing, again looking at the halo rather than the inner galaxy. The cool thing about this project was that they then worked out, given the selection function for their stars and given where they were located, they could integrate across, you know, a range of distances in the Milky Way and try to work out across all of that space how much of the mass came from globular clusters versus other normal sources of stars. Yeah.
Is this ceiling at nitrogen to iron of 1 is this physical, or is this?
No, that'll be one of the signatures of large survey abundance analysis. Yeah, there's some, particularly in the light elements, the apogee abundances are tricky to use correctly. They don't get, and I'll mention this later, but you know, every survey has things it can measure well and poorly. And yeah, a lot of, yeah, as Yanis will know from working on GALAH, when you're trying to process quite a lot of stars at the same time, sometimes you wind up with edges to your allowable answers. So it could be that the nitrogens are actually higher than that. Yeah.
Can I also
Yeah.
ask a question? So, and this is very naive because I'm not in this field, but you claim that this particular abundance makes it look like a globular cluster population. Is there nowhere else in the galaxy that you find those abundances then?
Yeah, so this gets tricky, right? There are 2 open clusters that appear to have this pattern. 6791 and Ruprecht 106, right? Or is Ruprecht 106 the globular that doesn't have it? Okay, there's one globular cluster that doesn't show this pattern. But it's a very old open cluster. Obviously, a few % of the halo has this pattern. So, is it just halo stars? Yeah.
It's a globular cluster star versus a halo star.
Yeah. So it's a little bit of a circular argument, and always has been. The only component of the Milky Way where this is a strong population is globular clusters. And earlier studies in dwarf galaxies basically didn't find any of these stars. But if they're a few %, you know, earlier high-resolution studies of dwarf galaxies had 30 stars in them. So you might have just missed it. So it's possible that they're formed not just in clusters, which would, you know, change all of this and require lots of follow-up work. But it's the only environment that we have that produces a lot of them.
I mean, do you see them also predominantly in streams?
Yes.
Coming from globular clusters, or do you see them also randomly distributed across?
Both. So people have gone and looked specifically, for example, at Palomar 5, which has these really well-populated tails, and that does show this abundance pattern. Some of the stars have this, and some of them are normal in that co-moving group of stars. But also, these stars that we're finding are just in the field. They're not necessarily associated to any kinematic structure. Yeah, which is a matter of time, right? If they truly came from clusters and they were in a tidal tail, that tidal tail will only last a few orbits, you know, in a spatially coherent way. And then they will sort of phase mix and end up all over the place. And so you could perhaps, like people have tried to look at whether you can still look in a kinematic space and attach individual stars to individual clusters. And that hasn't worked very well. But also, the integrals of motion aren't conserved over the entire history of the Milky Way. So you wouldn't necessarily expect things that were, you know, stars that were lost from clusters a long time ago to have stayed in the same orbit as the cluster over all that time. Yeah, so the first thing we see is that, you know, a few %, no matter which survey you look at and no matter which abundance pair you choose, a few % of the field looks like it has these abundance patterns. And so we said, well, that means they came from clusters. And then we said, but what does that mean, right? If your stars are, if your globular clusters are half and half, normal abundance, weird abundance, hey, 4% of the halo came from clusters, right? So you've got your 2% that's chemically weird and your 2% that's invisible, abundance-wise. And that's fine, that's not a big deal. One of our follow-up observing proposals came back with a comment that everyone knows the halo was accreted. Why are you looking at this? This can't possibly be what's there. I think we've made a little progress on general acceptance of this idea since then. But the problem is that although I said we don't have a good model for forming globular clusters, we have a lot of different ideas, almost all of which require that originally there were a lot more stars in the cluster. If you're going to do chemical feedback from a star, from like an AGV star, or probably not a supernova because the metallicities don't change, you're only going to get a fraction of that star's mass back into the ISM, right? And so if you're going to form a set of stars from that, or influenced heavily by that, you need quite a lot of those original stars to produce the polluting material that then becomes your next set of stars. And so we all have this mental picture that there are actually quite a lot of these first generation stars that then vanish before the present day, because now we have basically balanced numbers, 50-50, you know, first and second group, normal and strange. And so if you count those stars, then there's a whole lot of abundance-wise perfectly normal stars that formed in clusters and then left. And we're hiding them in the halo, and we just haven't been paying attention to them. Visually, if we're looking for the yellow ones, right, and our clusters now are 50-50, then every yellow one we find corresponds to a blue one. But if the actual original situation was like this, every yellow one we find corresponds to, you know, 6 blue ones, 10 blue ones. And so when you run the numbers, you get a whole bunch of different possible fractions of the halo that came out of globular clusters. And this is the part that starts to get upsetting to the everyone knows the halo was accreted people. So this is from a semi-analytic simulation that tried to put globular cluster formation into a suite of models that were trying to reproduce the Milky Way-like galaxies. And so they said if we put in globular clusters in a way that we think is a reasonable way to form them, and then we look at how often they dissolve, how often they lose mass, what fraction of stars in the halo would have come from those clusters. And so they come out with a few percent, complete total altogether, not chemically different, just everything you get from globular clusters is 2%. And they add this red line, which is from a Sloan follow-up paper, where we said that it was actually more like 10% altogether. So we have that 2% that are chemically distinct, and then they bring their friends from that invisible first population. But other studies have found, observational studies have found other numbers. So that Horta study that integrated the mass, you know, have between sort of 4% and 10%. The Skiavon study that looked at the inner galaxies, similar range. Our apogee study, the lower limit's actually quite high. And then the original study, we said, hey, as much as half the halo could have come out of globular clusters if we believe these really extreme cluster formation models. And that was provocative, right? The point of this was to say you can't just ignore these guys. Like, obviously half the halo is too much. But given the models that we have, it's allowed. So we need to look at those models. We need to figure out, like, how many original first population of stars do you actually need in these clusters? Because they don't just disappear, right? They have to go somewhere. They have to go into the halo.
Is x-axis different simulation?
Yeah, so this is our 25 different Milky Ways. Sorry about that. So one of the challenges of this is that we don't have a complete picture. No one actually knows everything there is about globular clusters. As I mentioned before, they've evolved a lot since they formed, so we don't know their original masses. There are people who will tell you they do. But of course we don't. They all have their own unique life histories. And so we can guess, but I don't know how good those guesses are. We're not always observing the whole abundance pattern. And we look at the stars in globular clusters now. The carbon-nitrogen anticorrelation always happens. The oxygen-sodium always happens, though with different levels of extent. The magnesium-aluminium doesn't always play along. The magnesium sometimes doesn't deplete very much, but we don't know why. So with the different observational data sets we have access to, we measure different parts of that pattern. So GALAH can't get oxygen for giants. The lines get really small and we can't measure them. Apogee can't do sodium. Oxygen, sodium is like the fundamental thing that people who look directly at the globular clusters look at. So already in the field, we can't do the one-to-one comparison that we want. So we take other elements, and because there's 6 of them in the pattern, you can take any 2 you like, or any 3 or whatever. But it's not the whole picture that you really want to have. And then also, we started out just looking at giants because we wanted halo stars. Gaia hadn't happened yet. We didn't really know where stars were in the galaxy. You just sort of said, look, if it's metal poor and it's out of the disk, it's probably the halo, because what else is it going to be? But we can do a much better job now of picking the kinematic halo rather than just, oh, it's far away, I reckon that's probably the halo. The samples from GALAH and Apogee are quite local, so we can get the local halo. Gaia distances are only good to a few kiloparsecs, but the disk halo separation is pretty easy even without a good distance, given the transverse velocities. You can usually do a pretty good job. And so one of the things that we haven't gotten into yet, but really ought to, is looking at dwarfs in the halo, because you can now, you don't have to look for giants, and to see if they follow the same pattern, because there's no reason they shouldn't. But in the globular clusters as well, all of this work is usually confined to giants because they're bright. They're the things we are easily observing. So there's a huge incompleteness in terms of just evolutionary phase that's going on there. So there's, even though we've been doing this for a long time, there's so much more to do, which I think is a common feature of observational astronomy. So one of the things that, so I said we don't have the full abundance pattern. When we go and try to actually correct that problem, fill in the rest of the abundances, we find that some of our stars that we thought were globular cluster stars aren't actually. So this is a result of some follow-up work across a number of observing projects, where we took our stars that are CN strong, which should have the anomalous abundance pattern. Those are in green, and our stars that should be CN normal, so they should have the normal abundance pattern, and looked at magnesium, aluminium, oxygen, sodium in all of them. And so if we were right about every star, the blue ones would be down here, and the green ones would be up there. And so clearly we're not right about all of them. We're not too wrong. But if I knock out the ones that are high metallicity, we're actually doing pretty well. So I think what's going on, well, these guys are maybe suspicious, but I think what's happened here is that we were a little too, what's the word I want? Like happy to select stars at high metallicity and say those are probably from clusters too. Because if we restrict ourselves to the low metallicity end of the set, it actually works pretty well. Like our carbon and nitrogen are echoed in the oxygen, sodium, magnesium, aluminium plane. So suggesting that the stars have the full abundance pattern really did come from clusters. But then we have to figure out, like, why are these more metal-rich stars having strong CN bands if they don't have the rest of the abundance pattern? You know, what is that? That is perhaps an entirely different thing that we also didn't know about when we started the project. So that bears further investigation, I think. Also, because there have been so many more of these stars found in the interim, it bears looking at as much of a full abundance pattern as we can for all of them to really confirm, lock down what we really think about them. So there's a number of ways we can continue to pursue this. I think looking for more of these stars is a good thing to do. Sarah Kane at Cambridge is using the Gaia spectra themselves, so the low-res XP spectra, again to find the CN and CH features, and making huge catalogs of interesting stars that appear to have a high nitrogen abundance. There's a guy called Dominic Wern who's at Liverpool, who's looking directly in the dwarf galaxies using apogee data. So we haven't seen these stars in these galaxies before, but like I said previously, when we've gone and looked at individual stars in detail in dwarf galaxies, they've been fairly small samples because they're pretty far away. So filling that out to be a larger sample, I think, will be a really interesting thing to look at. Thanks. Since Gaia, right, we've realized that the halo is actually quite full of kinematic substructure. And a lot of it's accretion, some of it's streams, and some of it's, we don't even know yet what exactly is going on kinematically, like how to read the complexity of that space. There are a lot of people who want to name different components of the Milky Way different things. I think the overall story makes sense, that there's early accretion, and the last major merger was about 8 billion years ago. Whatever you want to call it, I don't care. But one of the things that's been pointed out by Vasily Blakharov in Cambridge is that a lot of the inner galaxy nitrogen-rich stars have similar orbits and metallicities to the stars that they think are that very early accretion phase. And so perhaps either globular clusters are all of early star formation, which would be cool, and I'd love to hear thoughts from the high redshift people, or very early star formation makes this abundance pattern without needing globular clusters, which would turn the whole thing upside down and be really fun to try to figure out how do we interpret it then, what does it mean? Like I said, we're looking directly at high redshift now, which you all know, obviously, and finding these very compact groups of stars. And so it's been suggested that those would go on to become present-day globular clusters, which would be very exciting. There's a lot of, like I said, they all have their own individual evolutionary path to get to the present day and not be destroyed and all of that. But it's the idea that you can look directly at that kind of redshift and see anything this small is just super exciting. And then there are simulations, including a Nature paper that came out yesterday, saying, oh, we can make these now, right? So simulators, now that we can see them at high redshift, now that we have some sort of target to aim for, are going into their models and seeing, like, what do they have that is giving compact and the right mass scale at the right time, which is really exciting. I think there's a really excellent cycle between, observations we don't understand, models that can try to produce them, that goes around, I think, really well to build our understanding of how anything works in the universe. So I'm excited to see where it goes. And I'm happy to talk to everybody about any of these things. So thanks.
So these oxygen-sodium anticorrelations within globular clusters, is there any spatial correlation with regards to where the stars are situated in the clusters?
Sometimes.
Sometimes.
Sometimes the anomalous ones are more centrally concentrated. I think that's generally true.
Okay.
Yeah, which sits well with the picture that it's like a second generation that formed sort of in the middle from material from the original stars.
Okay.
Yeah, but the observations of the very core are all HSC, and the observations of the outskirts are usually not. And we don't have the continuous coverage because the field of view is very small for the space observations. But it's the only way to get into that very dense region. Yeah. Yep.
Yeah, I'm of course interested in how do you connect these high redshift ones and low redshift or local globular clusters. So you cannot see them anywhere else but our Milky Way with to study the abundance patterns, right?
So Søren Larsen in the Netherlands somewhere does individual stars in local group dwarfs, globular clusters. It's very hard work. And the integrated light signals are very hard to figure out like how to interpret, because you're mixing strong lines and weak lines. And so you get a medium line, and what does that mean?
Okay.
Yeah.
And I mean, to me it's a little bit, of course they must be there at early times, right? You see them with these very old stellar populations.
Yeah.
How else are you going to form them? But I'm still puzzled as to why do they not get destroyed? I guess they're just so compact that you just will destroy them or something. What is your thought on that?
So the people who look at normal star clusters find that lots of them get destroyed, right? So I'm thinking studies of star clusters in the disks of galaxies, right? And there's a mass function for the clusters with the slope, and the low mass end, gets formed and then gets sort of pulled over into this sort of shape like that. And so people have suggested that at the time we're forming globular clusters, maybe we made a lot of really low mass ones too. Maybe cluster formation is a generic process and there's not a special thing about globular clusters. And that would produce lots of stars at very early times that then become unbound and just become the fields of galaxies.
But then you would have to form a lot of them at very early times,
Yeah, yeah.
right? Which, and you know, the ones that survive tend to be the ones that are more compact and more massive,
Yep,
right?
yep.
And so I guess we would see them, start seeing them now, and
I mean, that would be great.
well, I'm not sure we do, right? We are seeing some, but we are definitely not seeing a lot more than
Right.
than what Milky Way has.
Oh,
So
that's a great question, actually, is how many should you have?
how many should you have if this is really if you're not forming them along the way? But then how do you form them along the way and have the ages that they have?
Yeah,
the
exactly.
rest of the time?
Yeah. It helps that the time step per redshift gets really small as you get that far back, right? So 13 billion years plus or minus 2 is actually a huge redshift range.
Yeah.
And so in, you know, from the age perspective, it's not that big of a difference. You know, that's about as well as we can fit an isochrone to a set of stars.
But 11 billion years is still quite far back.
Yeah. So I think up until this point, the explanation has been, well, they're too faint, so whatever, we can't see them. Well, anything the size of a globular cluster is too faint to be seen at, you know, redshift 3, so we don't worry about it. But now that we can see them directly at 10, I think there are a lot of interesting questions about what are the limits on what you can see at that redshift, like how bright does it really have to be, and how much of a low end of the mass function could you hide in the lensing observations?
Yeah, we need to study completeness better, but I think that scenario is, you know, it's exactly the very compact, very, very massive ones that would survive, and those are the ones that
Yeah.
are the easiest to observe for us,
Yeah.
because that's exactly the sweet spot for lensing, so.
Yeah. Yeah.
It's going to be exciting, but I think we're still missing a big picture here.
Oh, sure, yeah. Yeah, there's lots of room observationally and in theory to hide a lot of small structure. Yeah.
So what if like you just count the number of globular cluster systems in other galaxies and you go out as high a redshift as you can, which I know is not going to be very far, but then could you in principle find some sort of destruction rate by seeing how, if you control, say, for a halo mass, how many globular cluster systems the galaxy has, and see if you can track the destruction rate.
I don't know if
you can actually, if it's a feasible measurement.
So I don't know if anyone's done that. The extragalactic studies have established that there's a nice relationship between the mass of the halo and the number of clusters that holds down to about the Milky Way. Low mass galaxies are a problem. The number of globular clusters there in dwarfs is kind of unpredictable, but for higher masses, and out to early types that are quite massive, there's a nice correspondence there, but I don't know that they've looked at the redshift evolution. I'm not sure that we get far enough away. We look at things like Coma and Virgo. That's probably not very far on you guys' scales.
Yeah, I mean, because like some of the things we're working on is like looking at globular cluster populations, like at redshift like 0.3, which is
Yeah.
Gets you a couple billion years, but I don't know if that's far enough. The completeness is for one very low.
Yeah.
Even that close, and then well close for.
Yeah.
And then so it's I don't know if the completeness limitation limits you too much to be able to constrain.
Yeah, it's an interesting thought. I mean, if the high mass end locks in and doesn't get destroyed for several billion years, that's actually really interesting. Because then all of the processes that cause stars to escape, they're not that strong, I guess, if they're operating, but they're not destroying them. Yeah.
Nick, you're doing this. Of course, those are galaxy clusters, though, so you have another environmental problem.
Well, you're in a very metal-poor environment where you form the cluster.
Yeah.
So there is absolutely no guarantee that the initial mass function will be the same as the local one. And so you're looking essentially at the tip of the iceberg normally with the observations. And so I just wonder, anybody did really deep bit skeptical maybe for ELT for that. I mean,
So people have done present-day mass functions for globular clusters,
okay.
but they are very affected by dynamical evolution. So mass
Right.
segregation is a huge factor.
Right.
And then the mass loss that does happen, the tidal losses and the evaporation take the low mass stars out first.
Right.
And so it's actually quite uncertain how to correct for that and get the initial mass function,
Oh,
even in the
that's
Milky
a
Way.
problem,
Yeah, I will say there was some really gorgeous JWST spectroscopy at redshift 2.5, which is not, I mean, it's far, but it's for you guys probably not that far, where they actually have a high enough resolution to see that they've got the emission lines that you would get from massive stars. So like the helium and the whatever. And this is part of where they get that idea about there's a lot of nitrogen happening in these systems. Yeah, I wish there was sodium in that spectral range for those stars, but I don't think we're seeing that.
Well, we also see a lot of that in very massive young clusters in the Milky Way. Westerland 1, which is by far the most massive, has a lot of sodium.
Oh, really?
It's debatable, is this observable in all of the stars or just the most massive stars?
Okay.
It doesn't have as much oxygen. So in oxygen it's somewhat above solar, and in nitrogen is way above solar.
Okay. Yeah, for a long time, the globular cluster people were like very against the idea that this is just cluster formation, right? And the young clusters could tell us anything. But I think we've all calmed down a little bit on that front.
So it could be just a correlation with how dense the environment is where the stars formed.
Yeah.
The other clusters is just what survived from those stars.
Yeah, which me of 10 years ago is horrified to hear me say, but yeah, sure. Lots of things could be true.